Now, law of conservation of angular momentum. Last time in the last video I have discussed, but still there is a topic, okay, angular momentum, that is law of conservation, and one example is there, okay, and we are discussing it with a girl sitting on a swivel chair, okay. Now, as you know, angular momentum about a fixed axis is given by L is equal to I omega, and if you take the time rate of change of angular momentum, then this becomes dl by dt. I is constant, so it becomes d omega by dt, and as you know, the rate of change of angular velocity gives you angular acceleration. So instead of this d omega by dt, we have written alpha, and as you know that I alpha is nothing but torque. Okay, so we can write tau is equal to I alpha, or we can say rate of change of angular momentum is equal to tau. Dl by dt is equal to torque tau. Okay. Now, if dl by dt is equal to 0, then we can say that if the differentiation of any quantity is 0, then that particular quantity must be constant. So, dl by dt, if it is 0, then L must be constant. Okay. So, what will happen? Omega will be constant. Okay, when dl by dt is constant, dl by dt is say 0, then L is constant. If L is constant, then omega is also constant, as we have L is equal to I omega. If L is constant, then omega will also be not changing, because I, that is moment of inertia, is a fixed quantity. Okay, so we can say omega is constant. So we can say that in the absence of resultant external torque, the total angular momentum of the rigid body remains constant. This is nothing but the law of conservation of momentum. There is one example. Suppose a girl seated on a swivel chair. If chair rotates rapidly and girl stretch her arm in horizontal, then the angular speed of the chair and the girl decreases, and if she folds her arm, then the speed increases. Try to understand. She is sitting on this chair. Okay, this chair is rotated. When you stretch your arm, then what will happen? The speed of the chair will decrease, and if these arms are folded and they are placed on the arms of the chair, okay, if you fold your arms and put them on the support which are there on the chair, then the speed increases. Okay, this is shown in the figure. Okay, let this occurrence can be analyzed by angular momentum. Suppose when the arms is close to the body, then moment of inertia is I1. Okay, what will happen? Try to understand. Moment of inertia here changes. When your arms are there on the supports of the chair or close to the body, then that mass of the arm is having less distance from the axis of rotation. So R is less. When the arms are stretched, then the mass here, that of the arm, is having greater distance from the axis of rotation. So according to the formula, I is equal to mr square, when your arms are stretched, then this moment of inertia increases, and that is why what will happen, as one quantity, that is, as you know, L is equal to I omega. Now this I increases, moment of inertia increases when your arms are stretched, then this omega reduces, angular speed reduces, and if your arms are there on the support, then the mass is close to the axis of rotation. Axis of rotation થી નજીક છે. Mass is close to the axis of rotation, and therefore the moment of inertia, as r is less, okay, when the arms are close to the body, r is less, then moment of inertia is less when your arms are close to the body. Okay, r is less, then moment of inertia will be less. Okay, therefore what will happen, to keep this L same as it was earlier, omega has to increase. Okay, and that happens in our day to day life in a practical. Okay, so let this occurrence can be analyzed by angular momentum. Okay, we consider that moment of inertia is I1 and angular velocity is omega 1. Angular velocity is omega 1, and when the both hands are horizontal stretched, we can say moment of inertia is I2, and what you call it, this must be I2. Okay, and angular velocity, okay, must be omega 2. Now as you know that according to law of conservation of momentum, this I1 omega 1 must be equal to I2 omega 2. As I1 is less than I2, okay, then omega 1 must be greater than omega 2. When the arms are close to the body, I1 is less than I2. It means that omega 1 must be greater than omega 2. Okay. Moreover, this law is used by circus acrobat and divers. Okay, divers which are diving, okay, in the swimming pool from the height. Moreover, this law are also used by skaters and dancers performing pirouette on the toes of one foot display mastery over this law. Okay. Now this is the another topic. Obtain the necessary condition VCM is equal to R omega for the rolling body without slipping. Now this body is rolling, means this goes from one place to the other place by rolling. Okay, it is not slipped. Okay, so it is performing the rotational motion about its center C. Okay, now see, this is a disc we consider. Okay, it is moving on a straight surface. Its center of mass is on the geometric center of the disc. Okay, and VCM is the velocity of the center of mass. So this is the place where the center of mass is located. It is parallel to the surface. The rotational motion of the disc is about axis which passes through center. So this is the center through which the axis goes inside the plane of the screen, and this is performing the rotational motion, and as it performs rotational motion, then it goes this way on this straight linear path, we can say. Okay, now there are different points here. P0, P1, P2 are the points on the disc which are shown in the figure. The velocity at these points are obtained the sum of the components of the vectors, and at P1 we can have VR plus VCM. Here VR is the velocity due to rotational motion, that is R omega. Okay, the resultant velocity will be R omega plus R omega. Okay, that is rotational motion is having its velocity VR as R omega. VCM is also moving at the same velocity, that is R omega. So it becomes R omega plus R omega because they are in the same direction. So VCM is also R omega. So V1 is 2 times R omega, and VCM you can say it is 2 R omega. The position vector of P2 is R. So linear velocity at that point P2 is also R omega. Say small r we are taking at point P2. Okay, here if you consider this point P2, then at this point the distance is small r. So distance is small r, then the velocity is small r omega. Now this small r omega is the what you call it, its linear velocity. Okay, now see that linear velocity Vr at that point P2 is equal to small r omega. Okay, and the VCM, that is center of mass, is moving with the velocity r omega. Okay, so the sum will be small r omega plus capital R omega. Now P0 is instantaneously at rest and the velocity will be Vr plus VCM. Here V0 is equal to 0 because instantaneously V0 is in contact with the ground. See, try to understand this. Okay, 0, that is P0 point, instantaneously is in contact with the ground. So instantaneously it can be considered to be having 0 velocity. So it will be having the velocity which is r omega. Okay, here we can say the value of this velocity at 0, V0 is Vr plus VCM, and that point is instantaneously is 0. So Vr plus VCM is equal to 0. So both will be opposite to each other, which are having same value. That is velocity due to rotational motion and velocity of center of mass, they will be having same values in opposite direction. P0 becomes, or it comes at rest due to resultant velocity at point P0 is 0. VCM is equal to r omega. This condition applies to all the rolling body. Try to understand, whenever there is a rolling body, the velocity of center of mass is nothing but, if you consider this as a radius, then velocity of center of mass is equal to always r omega, and this is your linear velocity of center of mass. So these all particles which are there on the rigid body are performing the circular motion about the axis of rotation, and the body as a whole performs the linear motion, which is having its linear velocity to be VCM, and that VCM is equal to r omega. Okay. Now there is another topic, derive an expression of kinetic energy and velocity on an inclined plane of inclination theta for a body rolling without sliding. Okay, so this is the slope on which this rigid body is rolling without sliding, it doesn't slip. Okay, radius of this rolling body is r, and the angle at which this plane is kept as theta. Mass of this body is say m. Due to gravitational force, mg force will be in the downward direction. Here there will be an angle of theta. This mg force is in downward direction, this angle is theta. So the component of mg force in this direction will be mg cos theta. And this side, if you want to take the other component, then that component will be mg sin theta. These are the things. This is a normal force opposite to mg cos theta, and these two forces, a normal force and mg cos theta, are equal in magnitude and opposite in direction. These are the things which can be understood from this particular figure. Now this body is performing two types of motion. It goes in this direction, so it is performing linear motion, and all these particles are also performing the rotational motion. So it is a combination of two motions, rotational motion plus the translational motion. So it will be having rotational kinetic energy and translational kinetic energy. If its linear speed of center of mass is VCM, then its translational kinetic energy will be 1/2 VCM square, and its rotational kinetic energy, if you have its angular speed, is omega, then the rotational kinetic energy will be 1 half I omega square, and this will be the translational kinetic energy 1 half mv square. Now as you know, I is equal to mk square, where k is the radius of gyration, and as you know, vcm is equal to r omega. So just combining these two things here, instead of this I we are writing mk square. So 1 half as it is, instead of this I it is written as mk square, and instead of this omega we have written vcm upon r. From this equation we can say omega is equal to vcm upon r. So instead of this omega we are writing vcm upon r, so square of it will give you vcm square upon r square. And here we are not changing anything, it is kept as it is, 1 half mvcm square. And you can take common now, 1 half mvcm square. You can see here there is 1 half vcm square. Here also 1 half m into vcm square, that can be taken common. Okay, so it is taken, and we have 1 plus k square upon r square is a formula of the total kinetic energy of the rolling body. It can be applied to any rolling body, that is disc, ring or a sphere. Now compare k with potential energy, kinetic energy. Try to understand, when this rolling body is here initially, then it will be having the potential energy to be mgh, and when it reaches here at the bottom of the inclined plane, then the total potential energy is converted into kinetic energy. Okay, and this kinetic energy is bifurcated into two parts. One is rotational kinetic energy and the other one is translational kinetic energy. So this total energy mgh is equal to whatever we have calculated as the kinetic energy, that is 1 half mvcm square 1 plus k square upon r square. So this must be equal to initial potential energy. Instead of vcm it is written as v. Okay, so 1 half mv square, okay, into 1 plus this k is different, it is radius of gyration. Try to understand. Okay, now if you make this v square as a subject of the formula, then this 2 will be multiplied here in this 2 mgh becomes, and here m will be cancelled out. So it becomes 2gh upon, it becomes 1 plus k square upon r square, and this will be the value of v square. And if you take the square root of it, okay, then you will be having v is equal to square root of 2gh upon 1 plus k square upon r square. So this equation can be obtained if you take the square root of it. Okay, here the theory part of this chapter number 7 is getting over. Try to see all these videos 2-3 times and note down very important points. Some questions are also there, very important. I have told you in the video. Those questions you write in your notebook and practice them. Next time we shall discuss some of the illustration and numerical. Okay, thank you very much.